first of all, I want to confirm the schedule with some students. Okay. Actually, before the lecture, I think there's one girl. I think you have been confirming with me, and this is, I think, in our schedule, 15th, right? 15th week, and our lecture will be ended 26th. This is June. And I am thinking about having discussion. How about having our examination on 2nd of July? Another exam. Yes. 3. Okay, so I have 2 options. One is 2nd of July, and another one probably in the beginning of the and on the following Tuesday.
Ah, okay. Seven.
Alright, so this schedule has been decided. I will try to make a proposal with our office and try to get the belt. Especially, I have been talking about the printed version of our slides. So try to take some warming up. Okay. So this is the date or schedule of our course. And what I want to have today. So this is actually sulfide mineral processing. And what is this? You still have memories? What is this? Well, actually, it's not the best answer I want to give. So what will be the proper or most attractive description of this one? What is this? What is this? Actually, I have been lecturing or I have been instructing for this one. This is third time. And I was describing this particle to be an ideal model for map making. So inside we are having for the inside map. So actually here was the most important intermediate product. What about this? What layer? Slag. Actually we have spent more than I think 10 hours in studying the slag and the map phase. So if we are making some summaries or some warming up about slag, what is slag? Especially when we are having a map. What is this? So when we are having this map phase, so what will be the description of the slag? Some general sentence, some short sentence. So what will be the slag type? First sentence. So if we are having map as a product, so what are we having for the slag? We are having iron and silver. So this is violet slag. And when we are having violet slag, we are always having iron as the dominant element. And we are adding silver oxide as plus. The reason of producing such a match is because of the presence of iron. There is a big possibility we are having magnetite. So we have two stages: smelting first, and we are going to have converting secondary. So this is something I want to remind you first. And actually, there's some other most important topic today and tomorrow. We will spend like 3 hours talking about another issue. So matte smelting, actually we are producing matte and we are having slag. So in the matte, what are we having? The dominant minerals or dominant element. In the matte, what are we having? Generally speaking, we are having copper sulfide and iron sulfides. Something else? Let's make a calcium mark here. And when we are producing the mat, we will have slag as a must. As a must. And here we have already taught. We will have violet slag as the dominant, right? Dominant, right? But besides violet slag, we are always having this very stable spinel phase. Okay, so this is what we have already known, and the temperature will be at 700 to 1300 degrees C. How about PS2 and PO2? Some ideas? Some ideas? Maybe. And minus 6 to minus better is minus 8 first and minus 6 which is 80F. And how about PO2? The same story, property minus 8 to 10 minus 6 ATF. So this is general chemical parameters for mat making. And in the beginning of this example, at the beginning of this topic, we have been talking about the copper. And when we are producing copper, what are we having as a byproduct? We are always having those technology metals. Actually, I have been, telling some stories. When I was studying abroad, there are some trucks, very big trucks. They have a copper smelter, and every 3 months, there will be one truck. There will be like 1 or 2 tons of gold. It will be transported to London. So we will always have like technology metals and PGMs. For example, we will having, here we will have gold, platinum, silver. So this is associated with copper minerals. And besides PGMs, we are always having telluride, selenium, even actually some more metals. Actually, I put some information we have indium sometimes. So those metals, actually, they are even more important. So I have been talking about the production from Vietnam, from Garfield, from Utah, from USA, and they are still having their own copper mine, and they are running the copper smelter. And they are not mainly going for copper. They are mainly going for PGMs and technology metals. So they are byproducts. So it's very important because this is the motivation, driving force of making copper from sulfide minerals. And another concern will be from this part. We are always having an idea that there will be pollutants. So this is why actually the name of our school will be School of Metallurgy and Environment. So there will always be arsenic, there will always be mercury, sulfur. So they are toxic elements. So when we are having our mat making, as we have been describing in the title. So when we are having the mat, when we are having mat slab, so how will we, or what will be the most suitable technology in recovering those PGMs, technology metals, and how can we get rid of those pollutants? So this is the problem. So today, actually, I want to try to have the topic is the title Behavior of Elements. So this is today's topic, and some old information or old knowledge from our concentrate. So in our concentrate, what are we having? The copper, the cathode. So this is the copper concentrate of copper ore, and besides copper, we have already known that there will be base metals, nickel, lead, zinc, and there will be some commodity metals, selenium, telluride, and there will be precious metals, and PGMs. So they are what we are having in the system. So metallurgists, especially copper metallurgists, we are not only producing copper, we are also producing technology metals. Probably like 5 years ago, there is only CRISPR in Indonesia, so you have very limited production of technology metals. And nowadays, you have more than 1 million tons of copper, so you have big portions of those metals. So you will have probably AI, you will have probably IT, a lot of new or industries will be cultivated and promoted in the future. And generally speaking, the behavior of our elements will be determined on actually several categories. So the most important thing is the element and compound properties. So this is very easy to understand. So what we are talking, we are starting from CuFeS2. What is this? Copper carrot. This is our original mineral of copper, right? And for the properties, how we are producing copper, we are adding two main raw materials besides concentrate. What are they? Flux. Good. Zinc oxide and second one will be we are adding two.
Oxygen.
Okay, very good. So we are adding only two raw materials. We are getting that. So we are using the properties. So first of all, when we are having our sulfur and we are having the oxygen, what are we having? We are having sulfur dioxide. So this is the gas phase. So it can be removed, right? So when this is the gas, it will enter the gas phase. And when we are having iron and when we are having oxygen, we are having iron oxides. And when we are having SiO2, we are having a slag. So this is the properties, right? And copper will stay firstly as sulfide, and secondly it will be Pertemuan. So this is element and compound properties. So this is compound properties and metal properties. So this is dominant. So when we are discussing about the behavior of elements, so the properties of the element itself and its formed compounds will be the preliminary one. Okay. Second category will be the process. I have several examples. So you have already got my slides. So if you are turning from several page stuff, you are finding I have a lot of examples from my own research. So this process dynamics. So those conditions will also make variations. And we are going to have one very important and very important and actually troublemaker, arsenic. You will take this as an example in the following one. Okay, so this is what we should have in our mind before we are having further discussion. First one, the element and compound properties. And second one, the technologies we are using. And dynamic, the processing parameters, what we are going to have. So this is something we should have in our mind firstly. And generally speaking, actually this is the knowledge, the experience we have already generated. First of all, let's try to check copper, precious metals, selenium, tellurium, nickel, lead. These will be in lead and metal. Okay, the story will be easier. Actually, if you are following the progress or the release from International Copper Study Group, you are finding some interesting information. There will be a lot of several copper mines, which is rich with molybdenum. Do you know what is this? Molybdenum. It will be used in alloy. It will be used in catalysts. It will be used in actually refractory materials. So this is a very important matter. But before 2020, no one is knowing that we are having this one in copper concentrate. But from 2020, there are 2 big mines in China, and one from Australia, one from Argentina. So we are having copper mines, which is rich with this one. So you will have an idea where MO or molybdenum will report to, and we are analyzing that. We are recovering it. So here we are knowing precious metals, lead, nickel, and selenium, tellurium. They will be in the metal phase, and some other elements like zinc, iron, cobalt. They will be in the slag. And actually, there are some descriptions. They are easily to be oxidized. Actually, recently, I have got one project from Congo. And that company has a big copper mine, and the copper mine is copper and cobalt coexisting. And you are knowing this is very expensive metal, and it's very rare. And they are using both fiber and hybrid technology in processing this copper concentrate. And I have been discussing with them, and I told them that when we are having copper in the metal phase, we are having a cobalt in the slag phase. So if we are using metallurgy, copper can be easily recycled, but the recycling of cobalt will be from the slag. So we are going to have a long flow sheet, and they agree with this, and we will try to make a flow sheet for the company in the following half a year. Okay, so this is something we are knowing. And the last one, volatilised one, which are easily going to the gas phase, so such as zinc, lead, arsenic, antimony. So try to check. So 1, 2, 3, 4, 5. There are 5 most important impurities in copper industry, and they will be organized. So if you have a mission from the company or from the supervisor, you are recovering bismuth. So what should you do? In the future, if you are getting a topic, you should recover the bismuth from the copper industry, from the copper process. What will be your general idea? What should you do?
During the fuel gas?
Yes? You follow the of gas and
Sorry.
observing it.
Absorbing the gas.
Observing the gas. Okay, so this is a good idea. I was thinking about this topic. How can we recover MO or molybdenum? And you can have this one as a pre-topic, and you can find some information afterwards, because this is going to be very hot and very important topic in copper industry. Okay. So after the general information, I have made a schematic. So raw materials, technologies, properties of the elements will all determine the behavior. For example, what are we having? We are having concentrate. They are solid ones. We are having reverse. They are solid ones. We are having flux. That flux is polyethylene oxide. Doesn't matter. So they are more complex. So when we are processing these determined technologies, we are adding flux, determined or preset temperature, and we are having such a system. What are we having? The mat of the copper at the bottom, right? The furnace. We are having the middle layer as the oxide. So it's slag phase. And we are having gas phase. Gas phase not only sulfur dioxide. We are using nitrogen or oxygen enriched air. So we are having oxygen. There will be some remaining oxygen, and even some metal sulfides, metal oxides. They can be volatilized. So in the gas phase, it's very complex. In the slag phase, it's also complex. But before this before today, we have been studying a lot of information about slag phase. And the most interesting part will be how we are knowing those partial behavior. And here, I have put something. So besides the dominant element, copper, iron, lead, sulfur, we are having PGMs, we are having lead, we are having acid as well. Now this is something we are knowing from experience. And in the future, if we are having similar topic, if you are having similar research project, so you will try to find out what will be the exactly ratio or exactly partial behavior. Okay. So this is something I want to talk. And this is from a textbook. The extractive metallurgy of copper. And if we are reading the first row of this table, what are you finding? We are finding there will be three important streams. The first one is matte, slag, volatiles. So volatiles will have two different streams. So it will be the dust and gas. So volatiles. The solid one will be dust. The gas phase will be gas. So we have two different streams. So if we are categorizing or concluding them into three streams, it's very interesting to follow that. Copper, mainly in matte phase. So this is what I was lecturing or what I was instructing. And there are like 100 engineers from industry. They are having lectures downstairs in 101. In 101, same site in this building. And I was telling them that when we are making a copper production process, if the recovery rate of copper is smaller than 98.3, you are losing money. So when you are having your copper recovery rate bigger than 98.3, you are making money, you are leading the game. Otherwise, you are losing that. And when we are having such a number, actually it's the properties. When we are having copper in the industry, in the system, the copper will follow mainly with the matte. And after that, it will go to the blister and go to the cathode. But actually last week, I was sharing my own research, right? There will be 1% of copper loss. And in total, actually all over the world, there were more than 3 million tons of copper. 3 million tons of copper. So that was a big number. So actually, this is also a good topic. For alkaline or alkaline earth metals, like aluminum, titanium, potassium, sodium. So they will be definitely in the slag phase. There's no exceptions. So they will be in the slag phase. And for PGMs, for precious metals, also. Actually, I was publishing a paper like 3 years ago. I was very interested with the behavior of metals in collecting PGMs. We have three options. We can use copper in extracting PGMs. We can use lead, and we can use matte. So three different options. Actually, this is from my own research. We have copper, we have matte, and besides copper and matte, we have another one. And all of them are used in the industry. And I want to know which one has the biggest capability. When we are recycling our cell phones, when we are recycling the copper mines, we need a big or good recovery of PGMs. And you can use lead as collector, copper as collector, matte as collector, and the solid solution or our conclusion is that when we are processing those PGMs in matte containing system, this guy is the best connector. If you are having matte, you are losing no PGMs. You are losing almost no PGMs. You can get almost 900% recovery. But if you are using this one, you are losing something. So this is number one, this is number two, and this is number 3. So very soon, in Indonesia, in India, in some other countries, you are going to build some secondary smelters, and you will have options to try to build up or try to get some information like that. So this is why here we are having math. We are getting good recovery of PCMs, and they are very simple. The first 3 rows: copper in matte, alkaline metals in slag, PCMs in matte. But for the following part, antimony, arsenic, bismuth, cobalt, they are having different behaviors, especially for antimony. So 1/3, 1/3, 1/3. So this is a problem, right? Actually, I was telling you that for metallurgists, we are creating some new phases, some new layers. If those elements are distributing evenly or averagely in different phases, we are making no jobs. We are making no jobs. What are we having? We are seeking for such a partial behavior. If something is enriched, the mission is calculated. If the element is distributing averagely, no, it's getting more complex. More complex. So bismuth, arsenic, antimony, cobalt, they have similar stories, stable stories. And for zinc, lead have similar stories. So knowing those behaviors is very important, because actually, like 15 years ago, when I was visiting some copper smelter in Europe, and I found that they are recovering like more than 11 different elements. 11 elements. So let's count them. 11 elements. So they are recovering copper. They are recovering sulfur. Very easy, right? So copper, sulfur, and they are recovering, like here, they are recovering bismuth, selenium, nickel, lead. Actually, all the elements listed on this table, they are recovering. But at that time in China, actually I was cooperating with actually almost all the copper smelters in China. We are recovering 7 elements. So 11 and 7. Is there any difference? Yes. Yes. If we are not recovering those elements will be lost in slag, will be lost in dust or gas. So we are losing that. They will vanish. So that was not a beauty. Not a beauty. So knowing the behaviors of elements is a fundamental level of recovering them. Okay. Now I have labeled, or I have connected some information, and we have got this slide. Nowadays, actually, probably it's quite small with size of the paper, but let's try to make some zoom in. So we are having several elements. For example, lead. So in the mineral, when we concentrate, lead will be in the form of lead sulfide, right? And with the effect of adding of oxygen, it will convert to oxides of metal. So let's say some dynamic. And if we are reading this figure, the y-axis is pressure, and x-axis is temperature, the processing temperature. So if we are putting the first line, so 1250, this is what we have been instructing, the temperature for copper making. So if we are having such a temperature, and we are reading that, there will be some partial pressure for lead sulfide. So which means when we are having partial pressures of some species, some compounds, it will move to the gas phase. And so does some oxides. In the future, some of you may have more information about the lead industry. In copper smelting process, the dust formation is around 4%. When you are adding 100 kilograms of copper concentrate, you are getting 4 kilograms of dust. But for lead smelting, you are starting with PBS. And when you are adding 100 kilograms of lead sulfide concentrate, we are getting at least 15 kilograms of dust. So that was different because this guy is very easy to go to the gas phase. Okay, so this is for lead, and we have zinc, we have arsenic. Let's try to read one by one. So here we have the same temperature, 1250. So what are we having? We are having zinc copperized, but with the presence of oxygen, zinc will not very easily vaporize, but it will have such tendency. And more interesting part will be this one. We are having arsenic, right? Arsenic, right? And I have been discussing with you if we can make our selections, of destinizing or putting our arsenic in some materials, in solid form, in solution form, or in gas form, which one is the best? Which one is the best for arsenic? In gas phase, solution phase, or solid forms? Solid, right? Because arsenic is so toxic, dangerous elements. So if we are having arsenic, our preference will be immobilizing arsenic in some solid minerals. And here, let's try to check. We have arsenic from metal oxides, sulfides. If we are plotting the temperature of copper making process, so this number means all arsenic containing species, they will boil. All arsenic related species, they are boiling. So they will have the 1 atm pressure. So what does it mean? When we are getting closer to a copper smelter, when you are getting closer to the furnace, the gas phase will contain arsenic. So always be very careful when you are working or getting close to the copper smelter, especially when you are going to the uptake. So this is a suggestion or warning I will make for my students. So when they are making some entrepreneurship or some job in copper smelter, stay away from the gas streams. It's very sensitive. Okay, this is for arsenic, and for antimony. Let's try to check it. Same story. Oxides will recognize. So this is 1, 2, 3, and I have put copper in the middle of the bottom row. So we are finding that at the temperature of copper making, nothing will be lost on gas phase. Copper, metallic form, oxides, sulfides, they will be in melted form or solid form. So there will be not too much loose. And for crystals, same story. So when we are having such a figure, so which one will be erased in of gas? Which one? Arsenic, right? Arsenic will be of gas. Antimony will be of gas. Lead will be of gas. Bismuth will be of gas. So I have always talking about there will be five impurities in copper making process, and they are listed here. Because if we are distributed everywhere, we cannot find very inefficient method in controlling them. Okay, so this is 5 impurities together with our target one. And let's try to take the example that I have already labeled here. Arsenic. If you are Googling, or if you are searching the papers with a keyword of arsenic, and the affiliation is CSU, there will be more than hundreds of papers. Arsenic. Like 20 years ago, we have made suggestions for the government. We should have very strict regulations for arsenic control. If we are liberating arsenic, we will have them in gas. And once arsenic is a gas, it will go to the river and the water. It will be everywhere. So people will get a lot of cancers, disease. So that was not something negative. But we are needing copper. We are needing copper. And they are associated. So this is the paper actually I got from Matthew. I'm talking about arsenic content in the concentrate. So you are finding the different portions containing more than 0.3, 0.15% of arsenic. So this one is even bigger. For arsenic concentration in copper concentrate, it's increased. Actually, I was joking several weeks ago and told you that the paper written by some Australian guy, they mentioned about the challenges and opportunities of copper industry, and I was telling that opportunity is theirs and challenges are ours, because this is one of the topics. So if you are treating such a problem, arsenic content in the concentration is always a big problem. It's always a big problem. Okay, let's try to take this one in details. I have rewrote this paper. So this is what we are having after decomposition, right? After the decomposition or deassociation of complex minerals, we are getting arsenic sulfides. And with the presence of oxygen, we are having either oxides. That arsenic has several different oxidation states. 2+, 3+, 5+. And the information are useful knowledge for you. So we are having high oxidation state of arsenic. The toxicity will decrease. When arsenic is low octane state, it's more dangerous. So this is an idea. And when arsenic is with high octane state and with lower octane state, this one is more stable. This is green line and the red line. So when it's at 5+, it will be more stable than 3+. So that's always a big topic: how to oxidize arsenic fastly and efficiently. And I have given some introductions or examples. So this is from the industry. And even though we have some knowledge that the distribution behavior of elements is very complex, the properties will make a difference. Technology will make a difference. Processing parameters will make a difference. So different reasons will co-determine that. So this is a random process. So they are producing 72% of grain of matte. And let's check it. So this is 83% in the dust in random. So this is design value, and this is real after practice of conversion. And only 5% will be the slab, and 10% will be the matte. So this is one data. And we have more. And before we are knowing, or before I am giving the result from our own research group, I want to share another paper. Actually, this is the paper you are reading from here, Journal of Hazardous Materials. So this is a very good journal, high reputation, just like Q1. And the first author actually is my classmate. It's my classmate. And she used to work in USTB in Beijing, University of Science and Technology of Beijing. And now she moved to our school. And she's working in school of metallurgy now. Actually, there's a good, this is a very good material for all of us. Warming up, what we are having. Okay, first of all, there are different dust blocks or dust regions. So this is for the raw materials. And let's read from here. So we are having matte smelting, matte converting, fine refining, electrical refining. So 3 furnaces, right? And 1 cell. This is what I was instructing. Smelting, converting, refining, biorefining, electrorefining. So this is the flow sheet. Flow sheet. And if we are checking this is talking about the efficient removal and recovery of arsenic from copper smelting process. And actually removal, recover of arsenic from the flue dust. So they are knowing, okay, when we are knowing arsenic will get increased in of gas, it will be the raw material. If we are having arsenic in the slab, you have other options. So this is the predetermined. And if we are having those materials for the concentrate, we are having the arsenic. And after batching, the smelting, so we have different parts. Especially, we are having the dust. The dust we are going for assimilating. So this is a slightly interesting part. And how we are removal and recover arsenic. Here is some materials or products with red color. So we are finding in the slab we are having arsenic, and they will be sold out as pellets. And this is the dust, the raw materials here. And beside the dust, the slab, we are having arsenic sulfide residue, gypsum, mineralization residue in acid making. So when we are producing sulfuric acid, we are also having those arsenic-rich materials, and they are toxic residues. Copper smelters are paying a lot of money. Like when you are processing 1 ton such materials, it was around 2,000 yuan. Some ideas? Some information? No? Okay. So besides these residues, in the electrorefining, we are also having slime and anode mud, which is rich with arsenic. So this is something I would like to recommend you for warming up. So read this through, and you are knowing what is happening for copper making. And before that, actually, I have a better illustration because some of you may get familiar with this flow sheet. Smelting, converting, biorefining, electrorefining, right? Refining. And this is the Sulfide process. So we are having EF, slag cleaning. So this is the main stages of copper making. And let's try to find the main paths of arsenic. So there is a big circulation. From smelting, from converting, there will be arsenic enriched in the chicken, there will be in gas phase. And get collected, and we are having as the main arsenic output. And after the hot cleaning, we are having the sulfuric acid. Second time, the arsenic should be controlled in the product and in the final gas. In the final gas, we are also having some arsenic enriched in the final snap. And besides that, this is something interesting. Three or 4 years ago, I was invited to organize or try to organize the standard for copper smelters in China. It's national standard. I'm writing something for the standard. And I have proposed that all copper smelters, this is pyro, this is the pyro, this is the pyro, and this is the hydro. And I am suggesting all copper smelters should have the second hydro unit. And the hydro unit is help in selective lineage of arsenic. Arsenic should be removed. Because there is a very zealous circulation of arsenic. It will go back. When arsenic is going back, this system will probably disable in the future. And I have some examples I can share in 10 minutes. Okay, 10 minutes break. 10 minutes break. Very simple, straightforward. When you are reading some textbook, when you are following some videos, you are following some lectures, you are getting knowledge. But when you are having knowledge, you need to solve problems. And after solving some problems, you are getting a diploma. So this is my thinking. And this is how I cooperate with my graduate students. And they will try to find a problem, either from industry, nor from academic. So some problem is still not solved. And for copper making, it's a very big industry. And what I have been mentioning, the recovery of this one is quite interesting. Try to generate or try to find some information about that. And another, more importantly, for today, for the lecture, arsenic. This is a topic not only in China, it's true. You know, when I was studying, I was reading hundreds of papers. And I know some very famous professors. Actually, from that time, 20 years ago, I was knowing there's a professor from Tokyo University, after Yazawa, and his name is Fujita, Professor Fujita. And he is an expert in arsenic oxidation. And I am knowing another professor from Canada. His name is David Dressinger, a very famous professor. And his invention, his contribution was how to immobilize arsenic. So this is a topic for more than 20 years. From Japan, Canada, American, actually they are developing countries, right? And now, actually, there are so many developing countries. We are the center of metallurgy, so we should also know how to get rid of those problems. So arsenic, 20 years ago, it can be a commercial product. Arsenic can be used for insects protection, because it has some kind of toxic, and it can be used in killing those insects or some bacteria. But nowadays, it's forbidden all over the world. But no one is using arsenic nowadays. And arsenic has been stated as the only element which has no market. Okay, so the story, the background is getting more obvious. Arsenic is associated with copper and will be liberated in the process and going to the gas phase. But there's no destination or there's no economic benefit. So if there's no economic benefit, businessmen will ignore about that. We'll stay away from that. So if businessmen are staying away from the arsenic, which means arsenic will be, distributing without any order. So it will have very serious impact in the downstreams. Some residents nearby who are using the same water, breathing the same air, is going to be a problem. Okay, so this is, actually I was giving lectures for international virtual course, and there are some officers from your government, from Indonesian government, and they were having questions regarding to arsenic. Okay, so this is some information I want to share with you. This is information. And if we are finding problems or some technical problems or some other problems we want to solve, the first one, what will be your thinking? So if I have already given such background, what should we do? Or what should we do? Do you have any ideas? General thinking. If there's no market for arsenic, and it will be immobilized, or it will be liberated in the process, what should we do? We can discuss with perhaps another manner. if we hide arsenic and there's no economic benefit, what should we do? That's a very dangerous element. What should we do?
By cleaning the dust.
Sorry,
By cleaning the dust.
by cleaning the rest.
Yes.
Yes. Good. Well, this is only let's say, the first step. I'm asking about what will be general principle of getting rid of arsenic problem. What should we do? Arsenic should have a home, right?
Yes.
We shouldn't liberate the arsenic and no actions anymore. And it will flow freely. It's going to be a big problem. What should we do? Sorry. Score that. Okay, yeah, that's good. So it's arsenate. So it's ferroarsenate, iron oxide and arsenic oxide. We can form very stable minerals. Very good. Score right. Good idea. Generally speaking, if we are knowing the problem, this is the solution from Fujita and from Dressinger, and also from actually my supervisors in CSU. They are prepared score light. So arsenic, sulfides in copper pyrite. After liberation, it will be oxides. And with oxides, we are preparing some minerals, oxide minerals, which minerals means it's stable in nature, right? Otherwise, it will be dissolved. So when we can find some arsenic-containing minerals in nature, we try to imitate the nature. We try to create such an atmosphere for the formation of scoria in lab or in the smelter. We are creating that. And some companies are doing that. Some companies, of course, not in Chile, they are making scoria. So this is one solution. That quite demanded. You are paying a lot. You're paying a lot of money. Okay. So let's try to summarize a little bit to my question. If we know that we do have arsenic and we cannot avoid this problem, right? Because we are needing copper, we are needing technology metals. So those copper concentrates should be processed. And once we are having arsenic, the most important thing in our mind will be how to immobilize our arsenic. It shouldn't be in the gas. It shouldn't be in the solution phase. It should be a solid form, and it should be cheap and stable. That was our thinking, right? And this is your mission. Nowadays, there is some kind of very promising directions, but not very well developed, and there's still a way to go. I do think it will be very important in the future. Okay. So after the streams of arsenic, we have made some very 1 hour discussions or introductions. I have some examples from our own research. This is my name, this is my supervisor. So you are finding that this is around 10 years ago. And this was a serious issue. And this is an annual arsenic balance. So within 1 year, how much arsenic is added and where are they going? This kind of summary is very important. And it should be public for society or corporate smelter. They should publish or they should share their arsenic balance to the society, to the government. Or this process should be monitored by the public. Double flash smelting plus converting. So 2 smelters or 2 furnaces. And let's try to read this table carefully. So try to be patient. This is actually 30% of master thesis. This is from one master thesis. And he summarized one double flash smelter, he summarized another copper smelter, and he made some suggestions. And after that, he got his diploma. So it's very good contribution. very important contribution. And he is awarded with diploma. So first of all, what are we having? We are having copper in concentrate 25%, and the flask smelting burners is running at 1200 AD. So this is what we have already known. And oxygen enrichment is 80, and metal grade 70. The slab iron-to ratio 1.3. So this is something, some information we have already had in our mind, right? So if we are making the arsenic balance in 1 year, so let's try to check the number. 55.93, 44.07. What is the total? 100. 100. What does it mean? When we are having the total amount of arsenic, we are not caring about the quantities. We are caring about the distribution ratio. The ratio is more important. Ratio is more important. And for the arsenic input, so this is painted in red. This is in line with copper concentrate. So 37, like 1/3 of arsenic is from concentrate. And 6%, 55%, they are from slag concentrate. They are from flue dust converting slag. And with such a circulation, which means they are internal materials. And we can interpret the red numbers, they are fresh arsenic, primary arsenic. They are added together with copper concentrate, just like our belly. We are eating fresh food. So this is in the fresh food. And there are some fat in my belly. So it's not circulation, right? These circulations. So if I am making such an example, if I want to keep my size, keep my weight, what should I do? Input equals to output. I am going to balance. I will be incredible, right? If I am eating more and I don't exercise, I will get fat and I will have big belly, right? And if I am keeping this direction, my health will be broken and I will be having a lot of problems, right? So same story with the copper smelter. And this is the fresh arsenic to the system. And 100%. After the first burners, when we are making the met, what will be the distribution? So 32, 4%, 13%, 48. In total, this is 100. 100 in, 100 out. But we should know their ratios. The ratios. First of all, which is largest? Smelting dust. Reasonable? Yes. This is the high temperature. With oxygen. Oxygen, high temperature. So arsenic and its compounds should vaporize. So this is in the smelting dust. So we are knowing that. Okay. So besides smelting dust, it's not 100%. There should be some other chemical reactions, as discussed later. So besides the biggest part, what is the second biggest? Slag. So slag is a phase in the name of oxides. Right? Right. So if we are having such an oxide phase, and arsenic will be oxidized, it seems that oxides is an ideal home or destination for arsenic oxides. It do have such a tendency because just like water, while water droplets, the best way, the best home for the water droplets will be to the ocean, right? It will be, next entropy increase. The second biggest. And besides, 1, 2, after decomposition, arsenic will have oxide forms, also sulfide forms, right? So there will be like 1/7 in the math phase. And this is from, we can combine this one and this one together. This is from off gas. Off gas will be washed by water. And after washing, just like the water, you are blowing some air into the water. Those dust will be connected and captured by the water. And after filtration, you are getting such a cake. Okay? So this is also in the flue dust. So 4%, 49%, and in fact like 55%, they are in dust. They are in dust. But this one can be separated as material streams. And this one is connected beforehand. So after the gas vaporizes from the furnace, temperature drop, those precipitations, those vapors will precipitate as particles and will drop as dust. And very fine particles, which cannot drop, it will be captured by the water and will be the cake. So this is the story. So when we are having such partial behavior, so this melting dust, it goes for fading. It will be returned to the furnace, to directly recycled, because besides the arsenic, they are also having copper inside. So this one will be directly go for as a secondaries. And for the smelting slag, the second biggest, what are we doing? Actually, that's the way we are doing that. All Chinese smelters, we are doing the slow cooling and grounding and flotation, so which is like cleaning. After the flotation, like 6% will be returned as the slag concentrate, and the tailings 26%. So they are filled out, which means actually this is one of the most important output. So when this number equals to this number, everything is good. It will be incredible. And 1 equals to output 1. The system will be balanced. So the value will be same. You will not get fat. But this number is smaller, right? So this one should be named as our output. But for this one, when you are actually you are not selling this one. When you are producing 1 ton of this scrap cake, you should pay 2,000 to another company in processing this one. So for corporate smelter, you cannot process this one. And for you have to sell this one out, or you have to pay some other companies in processing this one. And this can also be our output, right? So in total, we have like 31, right? 31, 37. Still have 6% difference, right? If you cannot find the destination, the value will be bigger. The system will be disabled. Okay. So let's try to check. So when we have 1/7 in the copper mat, and after second furnace, this one will be divided into 1, 2, 3. 3 different streams. The biggest one will be in blister copper, second one will be in slag, and will be in the dust. So this one will also be returned. Both slag will be returned, the converting dust, 50% will be to the first smelting furnace. Another 50% will go to the second furnace. So they are used as secondaries. But in this part, there is no outputs of arsenic. Everything is recycled. This is important intermediate product. So 7%. So let's try to have the understanding. So here, 1/4 of the arsenic is removed, or 1/3. And after the second furnace, 50% of the arsenic is removed from copper. This is the copper, right?
Yes.
And 50% is removed from copper. And third furnace, pyrometallurgy, or the third furnace, pyrorefining, 7.3. What does it mean? You are not removing arsenic anymore. Arsenic is so stable in copper. So you have no idea how can we get rid of that. So when arsenic moves together with copper, you have to go to the electrical refining. So you are going to this part, and 7% will enter this part. So for the copper cathode, very small, because this is a very pure copper, 49 and 35. So this is copper cathode. And for the N5, and black copper. Black copper actually is refined in the process. Arsenic will be part of here. So nowadays, they are also sending this one out. Some other company, they can take these materials away without any payment. We have copper here, right? Copper is money. So the copper covers the processing fee of arsenic. So this is what they are doing. So 1, 2, 3, copper total here. Almost equals to this number, right? So this is how they are balancing their arsenic 10 years ago. And this is distribution. This is very good mathematic, very good way of presenting arsenic balance in a smelter. So try to have such an idea in the future. If some of you are doing similar research, I will recommend this kind of presenting. It's very straightforward and understandable. And there is very important conditions, parameters. The arsenic in the concentrate is only 0.38%. If we are processing copper concentrate with higher arsenic content, what happens? All the sections will be enlarged. This one will be a problem. You are no longer producing copper cathode with qualified composition. You are losing the quality of here. And the system will be, let's say, will erupt. This is the problem. So this is why we should control the copper arsenic content in the copper concentrate. Okay, the story is here. This is the best copper making technology nowadays in the world. The best one. Or one of the best one. For the best one. If nowadays we are knowing, okay, we have million solutions. The arsenic built cake, the millions black copper. What should we do? If this value increase, what should we do? What should we do? What should we do? I was talking from half an hour ago. I was talking when I am organizing or when I am proposing the standards for copper smelter process, and I am recommending that all copper smelter should build up a hydro-metallurgy unit. They are no longer returning their smelting dust directly. They don't return directly. They are leaching the arsenic out. They should decrease the values here. You got an idea? So if we are having higher arsenic content, arsenic should not be circulated so suddenly. You should reduce the values, especially here. You are not returning all arsenic back. You can return part of it. But here, not all of that. So this is why I am recommending that all copper smelter, they should have a dust leaching unit. Try to remove their arsenic. And this will help for the balance of arsenic. So this is a very straightforward idea, right? And after that, what should you do? You should have studies how to remove and recover the arsenic in the smelting dust. And this is a paper. This is a paper. Journal of Hazardous Materials, Professor John. I think she is quite good with metallurgy. My classmate. Same idea, right? You are knowing, okay, this is the only way we scan balance arsenic. So you are going for this study. So you are taking the dust of the raw material. You are removing the arsenic. So this paper is published in 2023, I think. 2023. So not very far ago. Actually, our paper has been listed as reference for this study. Okay, another information I want to share with you. Besides returning the dust to the furnace, this is very straightforward. We can leach arsenic from the dust and reduce the return arsenic to the system. Another issue is that whether we have solutions in increasing this value, this is much better, right? Much better. This is the direction I am going. And nowadays, there is one copper smelter, and we are having projects together. They are having this value of 60. Wonderful idea, wonderful result. Nowadays, the arsenic in the tailings can be 60, which means they can push this value doubled. They can have poor food or poor concentrate. They can get this system going very well. So this is my thinking. Suggestion is here, but we should make innovations here, both in this part and this part. So when we have innovation in these two parts, we are increasing the value here. So when you are removing 60% of the arsenic from here, everything is fine. Everything is fine. Very short process, right? Straightforward. And this is happening. Probably in the future, we are obviously promoting this technology all over the world. Another, actually, as I mentioned, this is from our master thesis. And the second figure is this one. Bottom blowing technologies. Another copper matte making technology. The temperature 1180 and saturation 1.8. The temperature is given, silicon oxidation is given. And for the raw materials, let's check it. Copper content, 14%. It's much lower than the copper concentrate. That's what we are having. They are having 1.5% arsenic. Actually, when we are reading such numbers, we will feel a little bit nervous. When you are liberating such a big amount of arsenic, the system will be very dirty, very dangerous. And besides that, the total value, like 6,000 tons of arsenic, several grams of arsenic that can kill people. This is 6,000 tons. So this is something very dangerous. And let's try to check what are we having. As I have mentioned, the behavior of elements will be determined by element and its compound properties, and also technologies. Same story. When we are having copper concentrate with very small copper concentration, and this is not only a copper smelter, this is a gold smelter. They are mixing copper concentrate and gold concentrate. And there is a reality when you are having gold concentrate, arsenic content is always several times larger than copper concentrate. When you are having gold, you are having arsenic. When arsenic is high, gold content is high. So this is nature. And when we are mixing gold and copper concentrate, the fresh or the primary arsenic is 85%. Like majority of the arsenic is from the primary one, and the secondary ones, slag concentrate through dust. This is oxygen enriched blowing furnace, another cement technologies. What are we finding? After matte making, we are having our matte is here. 2%. Previously, it was 14%. So 7 times larger than this one. And for the slag, less than 10%. And previous double flash, 1/3, right? 30%. And where are the rest? They are water test. They are enough gas. So the water from gas, EP from dust, electric precipitation, the dust, and back to the dust. So they are dust. The 90% are dust. 10% will go for melted phases. Very big difference, right? Previously, there's only 50%, and now it's 90%. This is a big difference, a big difference. And for those dust, only some of them are returned. So 2% sold out. If you fluid dust, different portions. And they will be, well, how should we process them? Should we return it? No way. No way. They are intermediate products. They should be stored with security, or they should be stored with a special place. It should be guided. It should be guided with armed person. And in those fluid dust is mainly arsenic oxide. Do you know Professor Chai Liyuan? Yes or no? Yes. Professor Chai. You should see his photo. He used to be the dean of our school and the vice president of CSU. And nowadays he is the president of Tianjin University. Do you know him? No? Okay. Probably he is the leading person in arsenic topics. He's the leading person. And he is also a metallurgist. And nowadays, he is leading a big team. I think more than 200 people. I mean, faculty members, master students, doctoral candidates, like around 200 students. They are doing some topic, doing some project together with one focus smelter. They are taking those dust of raw materials and they are converting them into arsenic metal. Because when we are having arsenic oxides, the volume is big and it's very reactive. And when we are turning it into metal piece, they'll be smaller. And actually, it is a very big project. And I heard it's like 100 million RMB. 100 million RMB try to convert oxide into metal. Very, very influencing project. Okay, so this is for the slag flotation. They will be returned. This will be returned. Here, 6.7, and these two per part will be returned, and the rest will be further processed. Okay, so this is something we are knowing, and the idea is that if this number keeps changing, it's going to be a problem. And we have some summaries for the bottom below. So this is arsenic distribution for the dust, like 90%. For the slag and the metal, only 10%. And if we are having these values, the total in the system will be like 6,000 tons. 6,000 tons. And let's try to talk about the reasons. And we have already known that those complex copper, arsenic, iron sulfides, they will decompose to simple ones, right? Simple ones. And this reaction will happen in a furnace. In double flash or E-flash reaction. the concentrate is added with this burner, and this space is a channel for oxygen. So oxygen is here, decomposition is here. So we are having actually oxygen sulfides here. This is most dense or most concentrated part of the region of the furnace, which is rich with sulfides and oxygen. If we have sulfides and oxygen, what will be the how to say, consequence, or what will be the following reactions? A lot of oxidation reaction will happen, right? So when you have sulfides, we have oxygen at high temperatures. Oxygen will react with our sulfides. So this is very intensive reactions in this region. So if we have oxidation reaction here, the energy is released. The temperature will keep increasing. So in this furnace, this portion or this part is the hottest one, and richest with our oxygen and materials. And we have plotted these two arrows. So this is high temperature, low temperature, high oxygen potential, low oxygen potential. Do you still memorize that? When we are oxidizing arsenic, when arsenic is in high oxygen state, probably for 5, they'll be more stable. And the formation of arsenic 5 will be accelerated with high temperature and high oxygen potential. So it will have less tendency to the gas phase. And another token here, this is the hottest region. And actually, before I'm talking to the details here, I want to have another very easy discussion with you. When you are, do you have any experience when you are moving to a place, a house, or some kind of place where a lot of dust, like PM10 or PM2.5, so you are getting uncomfortable feelings with your breath, right?
Yes.
So what will be the easiest way in lowering down the PM10, PM2.5? How to eliminate those suspended particles? What should we do? The easiest way. Sorry.
Absorb it by water.
Very good. You are giving the answer too fast. And I want to have some answers to be the bridge. Okay. You are spraying some water droplets. It is one. When you have a very small water droplets, those small particles will be absorbed and they will settle down. This is very interesting, very important phenomenon. And when we are having constructions, we are having some setups. Those water droplets, they are helping us. And here, same story. Okay, pay attention. We are having hypochlorite. We are having actually arsenic-rich sulfides. They are very fine particles, 13 micrometers. And after decomposition, they will be smaller. So those particles at high temperatures, they will be droplets. They'll melt. They'll be droplets. And here we just can imagine in this reaction shaft, there are rings of melt droplets. There are rings of slag droplets, right? Very heavy rings here. So small droplets. So when we're having numerous droplets of melt and slags, the interactions between gas droplets will be very good. Very good. So there is one good way for the dissolution. Arsenic is of gas, right?
Yes.
The of gas is surrounded by droplets of melt, droplets of arsenic, or droplets of slag. So the arsenic containing arsenic gases, they will penetrate into our slag, the mat. So it will be very close to equilibrium. Because for the slag, it was oxides. Oxides go to oxides. And for the mat phase, arsenic is very close with copper. With copper. So they have tendencies. So this is very close with equilibrium, and they are moving along during the settling. So this is why after entering this settler, actually the solubility or the dissolving of arsenic in the mat, in the slag, is close to equilibrium. So this is in this furnace. And for the bottom blowing, let's try to check it one more time. So same reactions. In this part, concentrate is added from the mouth. Oxygen is ejected from the bottom. So oxygen is here. Sulfide is here. The reaction will happen together with oxygen. Where is oxygen? Where is oxidation reactions? Where is the energy? Where is high temperature? So this is the sequence. So we are having oxygen here. We are having oxidation reactions here. We are having the high temperature here. The temperature here is high, and for the adding is low. Oxygen will be consumed here. So the oxygen concentration in the gas region is lower than here. So when we have low oxygen concentration, we'll have low temperature. The conversation will happen, but after forming arsenic sulfides, low oxidation state of arsenic oxides, they will have a shortcut and go to off gas directly. So after decomposition and slightly oxidized, they are going for the slag. They are going for the off gas, and you are collecting them as dust. So very simple, and this is very far from equilibrium. So this is why we are having like one third, several times. Actually, I am invited to be a committee member in deciding the knowledge, and I am always proposing this one. Because arsenic is the bottleneck of the process. If arsenic cannot be solved, the copper process will be stopped. And for flash smelting, we are having a slag phase, very good dissolving for capturing of arsenic in the tailings. And nowadays, we can push, or we can allocate more than 60% of the arsenic in the slag. So this is very nice. But there's another direction. As I mentioned, the president of Tianjin University, actually our leader as well, and they are going for this direction, and they push the arsenic to the off gas, and after the connecting of the arsenic-rich dust, they are producing metallic arsenic. So this is another direction. And let's try to make some discussions. So two different technologies. One is flash, bottom blowing is fast smelting, actually. Okay, let's try to pick up tomorrow morning. This is a good topic and very important. So do not be absent from the lecture. Okay, tomorrow.